Okay, so in the last lecture we were talking about Kas and Kbs, and we were calculating them using the dissociation constant for water. And this time what we're going to do is we're going to use equilibrium expressions to calculate those Kas and Kbs. So we're going to continue working in measures of those strengths of acids and bases, which are the Kas and Kbs. So we could have a problem like this, which is asking us about vinegar. We know that it is an equilibrium that's set up because this is going to be a weak acid. So what we need to do is consider what a balanced chemical equation would look like for this reaction. So they have given us the information that we need in order to describe this weak acid equilibrium. So they start off by saying we've got some amount of acetate. We are going to add that with water, and after we add it together with water, we're expecting that a small fraction of the H's on the acetate are going to jump onto the water, forming H3Os, and what's going to remain is some small fraction of CH3COOs in solution. So we can describe this in terms of an equilibrium system where we have a K, which is going to be for products over reactants. And because we're describing products and reactants in an acidic situation, we're going to call this a Ka. So we can put more specifics on this. We're going to say that the products are going to be H3O plus and CH3COO minus. We don't have any coefficients out front. This is already a nice balanced chemical equation. We're going to say the reactants. We are going to have CH3COOH. This was going to be aqueous. Now that water, H2O, is a liquid. Liquids don't count when we draw these expressions, so it's probably important to make sure we recognize what is in the aqueous phase. So we're going to leave the water out. That's just going to be a 1, and so this is going to be the type of expression that we have. So if we want to calculate the Ka, we need to substitute in the values based on what they gave us in the problem. So they've given us the H3O plus concentration. It's going to be identical to the CH3COO2 minus, and they've given that to us here, so we're going to put that in on the top line. So that's going to be 0.00118 times that exact same number, because it's the same concentration for both of those products. And then for the starting material, those reactants, we started out with 0.0787 molar acetic acid. So our calculator is going to give us a number like 1.76925. That's not keeping track of our sig figs. We have 3 sig figs in the numbers that we were working on, so let's change that to 3 sig figs. 1.77 times 10 to the minus 5. And so with a Ka times 10 to the minus 5, that's closer to 1, so this is saying that this still is an acid. This isn't a base, so that number makes sense. So now we have a Ka that we've calculated based on those concentrations. And we have that worked out for you as well in a typed out form. So more examples. We can calculate equilibrium concentrations so long as we have a Ka or a Kb for an acid or a base respectively. So let's work through some of these examples. So this first example up here is actually going to be another acetic acid example. So CH3CO2H is acetic acid, so we can write this out as CH3COOH is the way that I'd prefer to write it out. That's aqueous. That's going to be added to water. When you add that to liquid water, you're going to get an equilibrium. That equilibrium is going to be H3O pluses that are aqueous plus some leftover conjugate base, which is going to be CH3COO minus, also aqueous. So we can set this up as an equilibrium expression with our products on the top and our reactants on the bottom, and then it's a matter of plugging in the numbers that they gave us in the problem. And these numbers are going to be different than on the previous slide, so we'll get a different answer. And so now I've plugged in those values. They gave us 1.34 times 10 to the minus 3 for the conjugate base, they gave us 1.34 times 10 to the minus 3. For the H3O plus, they gave us 9.866 times 10 to the minus 2. And so now it's just a matter of crunching that on our calculator. Our calculator says something like 1.81998 times 10 to the minus 5, and that's not keeping track of our sig figs. We had a minimum of 3 sig figs, so let's change that to 1.82 times 10 to the minus 5, and so that is going to be the Ka for the weak acid, which is acetate. So CH3CO2H is the way that they like to spell that out. So I'm going to erase this slide, and then let's work on problem B. So now let's look at the next example. In this example, they are going to ask us about a weak base, which is going to be ClO-, and they are going to leave it up to us to figure out what this equation is. So based on the information that they gave us, they said we're interested in ClO-, it's going to be on the left. It's going to produce hydroxide ions, so that should be on the right side. It's going to produce HClO on the right side, so let's go ahead and put that over there. And then the starting concentration that they gave us was for ClO-, and so that's again going to be on the left side. It's going to pull a proton off of water. That's going to give us the OH, which means this is a basic solution. So we should be calculating a Kb in this case, and we can set up the Kb equilibrium expression. And so we've done that. We've put our products on the top, our reactant on the bottom, keeping in mind H2O as a liquid doesn't get to be part of this expression, it's just a 1. And so now we're just going to substitute in those numbers that they gave us in the problem. And now it's just a matter of punching that into our calculators to figure out what our Kb is going to be. We solved that, and our calculator says 3.4871, something really big. We want to correct that for a number of sig figs. I see a 4.0, so let's change that to 3.5 times 10 to the minus 7 would be the final answer. So now I'm going to erase this, and we will point our attention toward the third example. So in this third example, we're still going to have to set up a balanced chemical equation, and so let's take a look at what that might look like, keeping in mind that we're producing H3O pluses, and we're going to be calculating a Ka for this reaction. So now we have a nice balanced chemical equation. We need to go ahead and realize that this is an acidic reaction, so we're going to be calculating a Ka. We can make an equilibrium expression for that with our products over our reactants. Once we have that expression, we can just plug in the values that they gave us in the problem. And so we have plugged that in, so we can just punch this into our calculator and see what we get. So our calculator gives us some number that's not paying attention to sig figs. I see 2 sig figs. Let's go ahead and change this to 1.8 times 10 to the minus 4, and so that is going to be our Ka. So in the slides, we've typed that out as well, so you can see it for the first problem, for the second problem, feel free to pause this as needed, and for that third problem. So if we're going to continue to do this, there are instances where they're not necessarily going to give you all those numbers where you're just solving for the missing part, right? You may actually need to set up and solve an ICE table in order to figure out what those equilibrium amounts are so that you can type it into the equilibrium expression, or that you can go backwards from an equilibrium expression to those individual values. So yes, we can do ICE charts. So we are able to find a Ka or Kb, we can calculate that from pH, right? And so if they just give us this question, it can seem really, really daunting. The pH of this solution is 1.92. What is the Ka for HF? And so we can actually break this down into steps, which shouldn't be a gigantic surprise to you because we try to convince you to use these certain processes, these certain steps, in order to be able to solve any problems, regardless of what the numbers are. So we need to have a balanced chemical equation, and so for HF, we've seen that before. we need to use that balanced chemical equation to get a Ka expression, and then I need concentrations to go into that Ka expression, and those are going to come from the ice table. So we'll see this again. So what we need is the problem. This is the problem that they originally gave us, pH. We need a balanced chemical equation, so we've got that nice balanced chemical equation. We need an equilibrium expression, so they've given us that equilibrium expression. We know how to do that from a balanced chemical equation. And so now what we need is to be able to use an ice table to get the rest of the information. So let's set up an ice table. So what I would like to do is to put that balanced chemical equation at the top of my ice table. And so now I have an area for my initial, my change, my equilibrium, and then we can do another row for our final. We have HF, which is aqueous, so I'm going to be able to put information in this column. H2O is a liquid, so I'm not going to have anything in this column. My F minus is also aqueous, so I can put things down in this column. And my H3O plus is going to go down here into this column. So at the initial starting point, I have HF, and so that is going to be 0.23 molar HF. The water doesn't count, and at time 0, this initial time point, I have 0 F minus and 0 H3O plus, right? There are no products yet because I'm at time 0. So some change is going to occur. This reaction is going to go forward because we need to produce some of those products. So when I do that, I'm going to subtract an X. I am going to add an X. I'm going to add an X. And now for my equilibrium line, I'm just going to bring everything down. This is now going to be 0.23 minus X. 0 plus X is an X. 0 plus X is an X. And so for this problem, I don't actually have to write out the equilibrium expression right now because they've given me a pH. pH in this problem has been set equal to 1.92. If I want to go from a pH to a proton concentration, if I want to get the H plus concentration, I'm just going to say 10 raised to the negative pH, and so when I do that, my calculator is going to say 0.012022, and that's going to be a molar concentration of H pluses. I want to keep in mind my sig figs. I had 3 sig figs over there, 0.0120 molar. So that's my proton concentration at equilibrium. I can go ahead and put that down here on my line, 0.0120 molar. If that's what X equals, then that means that I also had 0.0120 molar here, and then my final concentration at equilibrium for HF is going to be 0.23 minus 0.0120. My calculator says 0.218, keeping in mind that I would much rather this be 0.22 based on my sig figs. And so I'm just going to write 0.22 because with my subtraction there, I was trying to use the least number of decimal places. And so that was the 2 and the 3. And so now I've got those final numbers. So ultimately what they want us to do is to figure out the Ka. So we're going to have to plug these values into that equilibrium expression. We've already written the equilibrium expression up here, so let me put those numbers in. My F minus, 0.0120. My H3O plus, 0.0120. My HF at equilibrium, 0.22. I'm going to use my calculator and find out this number. My calculator gives me a large number, 6.5454. I'm going to use the correct number of sig figs. We'll go with 2 this time, and so that's going to be 6.5 times 10 to the minus 4. So ultimately we were looking for a Ka, and this is the Ka for HF. And so this is a written out version. Of course, you see that they were using a different number of sig figs, so they got an answer of 6.61 instead of the 6.5 that we got, but it's still times 10 to the minus 4. So instead of using a pH, which is an indication of how strong an acid or base is, we can also talk about trying to find a Ka, Kb from the percent ionization, because that's one more way to indicate the strength. So again, just from the get-go, it is going to seem very daunting to see a question that asks you to determine the KB with what doesn't seem like enough information. But we can actually break this down, like we do, into the different steps. We need a balanced chemical equation, we need a KB expression, we need to understand the concentrations from an ice table of what's going to go into the KB expression. So let's start to work through those steps. Let's go ahead and do the balanced chemical equation for NO2 in water. They've given us the KB here, and so we're putting this balanced chemical equation in terms of a base. So we have NO2 minus, which is going to be looking to pick up a proton. It has to do that from water, so ultimately we end up with HNO2, which is now neutral, and OH minus, which is going to be contributing to the alkalinity or basicity of the solution. So now we have that balanced chemical equation. We can go ahead and use this as the basis for our ice table. So we have an initial, a change, an equilibrium, and a final. And so we also know that this aqueous is going to come down. This water is a liquid, so we're not going to do anything there. HNO2 can come down. OH, we can definitely put values in there. So this is saying that we started off with a 0.10 molar solution, and so that's going to be the initial concentration of our NO2 minus. Initially, we're going to have 0.10 molar NO2 minus. That's the way the solution started off, and then at time 0 we are going to have 0 of our products. This means this thing is going to proceed in the forward direction. That means that we're going to add products plus X plus X. We're going to subtract reactants. We have no coefficients here, so it's just all 1x's. We're going to carry that down to the equilibrium. We're going to say 0.10 minus x. We're going to say 0 plus x is just x, 0 plus x is just x, and so we've carried that down. And so now, just like we did last time, we didn't have to write the equilibrium expression to get this next part. We're going to take that percent ionization and figure out what our equilibrium concentrations actually were. So if you recall the way we calculate percent ionization, it's going to be the part divided by the whole times 100. The part in this case is, what did we produce? We produced OH minuses, and there's going to be some small fraction of OH minuses that came at equilibrium from that starting amount of NO2 minus. So we can work backwards, and we can say if this whole thing times 100 equals 0.015%, we can divide both sides of this by 100. So that is going to make it an even smaller number. It's now 1.5 times 10 to the minus 5. And so now when we look at this, we can plug in the NO2 concentration that we started off with at time 0, because we started with 0.10 molar NO2 minus. So now we have 2 of the 3 puzzle pieces we need. All we have to do is multiply both sides by 0.10, and we'll get the OH concentration at equilibrium. And so our calculator is going to tell us that by multiplying by 0.1, we're just going to end up with an additional digit in that exponent. So now it's 1.5 times 10 to the negative 6. And if that is my equilibrium OH concentration, I can move that over into my table. If I move it over for the OH, it's going to be the exact same number for the HNO2, and then it's going to be 0.10 times that number in order to get the initial starting concentration of NO2. And so I've written that out on my calculator so that you can see that there are a lot of numbers and that there was actually some small number that we subtracted from 0.100. But as you'll see here in a second, when we apply the number of sig figs, we need to have 2 sig figs. And so when we do that, it's going to be this, rounded up, and so it's actually just going to go back to that 0.10. So because such a small amount of this actually ionized, once we correct for sig figs, it looks like almost nothing ionized. So this is going to be seriously weak because we ended up with that number. And so now we can go ahead and solve for the KB expression. So when I write out the equilibrium expression, I definitely have my products on the top, my reactant on the bottom. The H2O liquid doesn't count. I plug in the numbers, 1.5 times 10 to the minus 6 for both on the top, and then 0.10 on the bottom, and my calculator gives me a value rounded for sig figs of 2.3 times 10 to the minus 11. And because the final answer was supposed to be what is the KB, we have now solved that. And so we've written that out for you, and just if you're using a different number of sig figs, you get a different number, right? They've got 2.25 here, but again, it's times 10 to the minus 11, so they're pretty much the same answer. All right, so now we've got another opportunity to try and find the pH of a solution. We're given a Ka, and so they've also given us the concentration. And so again, don't panic. They give you this nice long wordy problem, but we're going to go through the steps of what we need to do in order to come up with an answer. It's going to require an ice table. Ice tables need balanced chemical equations, and we can do all of this together. So now we have a nice balanced chemical equation. This is an acid. We're expecting that when you mix it with water, we're going to lose a proton. That proton is going to go on to the water to become an H3O plus molecule, and so now we can use this as the basis for our ice table if we have the initial, the change, the equilibrium, and the final, keeping in mind that that H2O is not going to be part of anything we're doing because it's a liquid. So now we look for the other information they give us. They've already given us a Ka, and so the other information that we have is a starting concentration for the solution. So that means that the C2H5CO2H was going to start off with 0.698. That means that our product started off with concentrations of 0. They're going to proceed to the right because there's no products. We want this thing to come to equilibrium, and so that means we're going to subtract an X. We're going to add an X. We are going to carry that down to the equilibrium line, 0.698 minus X, and then we can also have a plus X and a plus X. And so now we have to again go back to the equation and say, what is it that they give us, and what can we do to try to find out the missing information? So at this point, they have given us a Ka, but they haven't given us a way to just figure out what, say, the concentration of protons is. So this time, the next step is going to be getting to the equilibrium expression. And so I've written that out. The Ka is going to be products over reactants. It's going to be C2H5COO minus times H3O plus over C2H5COOH. And so this time what we're going to do is we're going to plug in our x's. So this is actually going to require us to do some algebra in order to solve what one of the x's is, and then we can go back and fill that into the ice table. And so now I've plugged in the x's based on what was in the ice table. So I've moved in an x and an x for each of the products, and then the reactant was 0.698 minus x. And so all of that is equal to the value that they gave me in the problem, which is 1.34 times 10 to the minus 5. So now it's a matter of having x's and numbers on the left and only numbers on the right, and so I'm going to need to rearrange this so that I can end up with something that I can solve for an x. So I'm going to write this out again so that I can have a little bit more space. What I need to do to both sides is actually multiply both sides by this expression, 0.698 minus x. So that I'll end up with an x squared over here, and I'm going to have to distribute this 1.34 times 10 to the minus 5 to both the 0.698 and to the minus x. So the distribution is going to say I need to multiply this and this. Now that I have distributed that, I have an x squared on the left. I have a number minus a coefficient in front of an x. So this is looking like it's going to be a quadratic equation if I can set all this equal to 0 and get all my numbers and x's on one side. And so I opted to actually bring everything on the right side over to the left side so that I didn't end up with a negative x squared out there in the front. So you could have done this either way, but I've gone ahead and done it this way. So now we've got this set equal to 0, so we're going to want to turn this into a quadratic formula so that we can solve it. So I've written out that formula for a quadratic equation, and then I've plugged in the numbers. And so you can solve this twice, once with the plus and once with the minus, or you can type this into your calculator, which you've hopefully went ahead and programmed to solve quadratic equations. And so when you do that, you're actually going to end up with two values for x. So when I use my quadratic equation solver, I get two answers. One is 0.003051, and if I look at my table, that makes sense, right? I'm going to have a positive concentration in the end. So I go ahead and put that positive concentration in the final line for my two products, and then I'm going to have to do the subtraction, 0.698 minus that x, minus 0.00305, in order to get the concentration of this acid at equilibrium. And I want to keep in mind my sig figs for subtraction is going to be 3 decimal places. 9 is going to tell me to round up, so my answer here is going to be 0.695 as that concentration at equilibrium for that acid. So now we've filled out the ice table, and we can go back and see what the question was asking us. The question was ultimately asking, what is the pH? That pH is going to be the negative log of the H3O plus concentration at equilibrium. So I need to do pH equals negative log of this concentration, 0.00305. And when I do that, my calculator says that my pH is going to be 2.51. And so that was a lot of work. We had to fill out the ice table in order to get the equilibrium concentration of H3O plus, and then we can use that in order to figure out what the pH is. And so on this slide, we've actually typed that out for you as well. And so this is going to conclude the lecture where we were doing some of these more sophisticated calculations using ice tables. And so now you're welcome to close this portion of the lecture and then move on to the next section.